Hello everyone and welcome. Now we are going to understand the methodology behind data science. By the end of this session, you will have a thorough understanding of analytics for data science, the analytics lifecycle, and all the critical technical processes that turn raw data into real insight. So let's get started. Let's begin with the first major topic, analytics for data science. Data analytics within data science involves using techniques from statistics and machine learning to interpret existing data and generate actionable insights. It helps us answer three fundamental questions. The first question is what happened? That's descriptive analytics. The second question is why did it happen? That's diagnostic analytics. And the third question is what will happen? That's predictive and prescriptive analysis. Analytics forms a core part of the broader data science field, which is focused on creating algorithms and models for future trends and complex systems. Now, and this is an important distinction, data scientists use analytics for cleaning data, evaluating it, and building models. Analysts, on the other hand, focus more on dashboards and reporting from structured data. Both roles rely heavily on programming, statistics, and visualization. They are related but not identical. Now, let me walk you through the four types of analytics in more detail, because this is a framework you will use throughout the entire career. Type 1, Descriptive Analytics. This summarizes past data. The classic question it answers is, what were our sales last quarter? You're describing what has already happened. Think of it as your rear view mirror. Now, coming to type 2, Diagnostic Analytics. This goes one step deeper and explains why something happened. Why did sales drop last quarter? You are looking for causes, correlations, and explanations. Now, you are not just looking in the rear view mirror, you are analyzing the road that you led you here. Type 3, Predictive Analytics. It forecasts future outcomes based on historical patterns. What will sales be next year? This is where machine learning model really come into play. They learn for past patterns to predict future behavior. Type 4, Prescriptive Analytics. This is the most advanced form. It does not just tell you what will happen, it recommends what you should do to achieve a desired outcome. How can we increase sales? This is where data science drives real business strategy. Think of these four as a progression from insight to foresight to action. Let's now look at how analytics functions within data science more broadly. The role of analytics is to provide the foundation, helping data scientists understand their data before building complex models. It also informs strategy because the insights from analytics shape the direction of further investigation. The core techniques used in analytics include statistical analysis, data mining, machine learning, and regression, A or B testing, which is widely used in product and marketing decisions, and data visualization through dashboards. The tools used are familiar ones: SQL for query databases, Python and R for statistical computing, Tableau for visualization, and Excel for quick analysis. And the skills required are statistics, programming, data cleaning, and interpretation. This combination of skills is exactly what we are building in this course. Now, let's clearly distinguish data analytics from data science, because these terms are often used interchangeably, but they are not the same. Data analytics focuses on existing data, answers specific and well defined questions, generates reports, and provides insights for immediate improvements. Think of dashboards, they are the output of data analytics. The scope is usually narrower and the timeline is immediate. Data science, on the other hand, it is a broader field. It involves the entire life cycle of data, creating new algorithms, building predictive models from scratch, and handling complex and often unstructured data like images, audio, and text. The goal is to discover new possibilities, not just answer known questions. The relationship between them is this: analytics is a crucial part of data science. Data scientists often perform analytics to prepare data for advanced modeling. So, analytics is a subset, an important foundational subset of the larger discipline of data science. Now let's discuss about the 5 V's of big data. The first one is volume and the second one is variety. Third one is velocity, fourth is value and fifth is validity or veracity. Volume is huge amount of data. Variety means different formats of data from various sources. Velocity means high speed of accumulation of data. And value means extract useful data. And validity or veracity means inconsistencies and uncertainty in data. Now, now let's look about the tools overview and examples of data analytics. These slides give us a visual overview of the analytics tools ecosystem and some real-world examples of data analytics in action. The tools range from SQL and Python at the programming layer to Tableau and Power BI at the visualization layer to specialized platforms like SAS and MATLAB for statistical modeling. What I want you to appreciate is that no single tool does everything. A professional data scientist or analyst selects the right tool for the right task, and knowing when to use which tool is itself a critical skill. Let's ground all of this with a real world examples. From the domain of marketing and sales analytics, one of the most data rich domains is business. Marketing analytics uses data to understand customer behavior, optimize advertising spend, and personalize customer experiences. For example, which customer segments are most likely to respond to a campaign? Which marketing channel delivers the best return or investment? Now, coming to sales analytics. Sales analytics uses historical transaction data to track performance against targets, identifying top performing products, and forecast future demands. Think of Amazon, how Amazon recommends products based on your browsing and purchase history. That's sales analytics powered by machine learning. These examples show how analytics directly drives revenue and growth. This is why businesses invest so heavily in data science talent. Now we arrive at one of the most important frameworks in this entire module, the data analytics lifecycle. The data analytics lifecycle is a structured framework that defines the end-to-end workflow of transforming raw data into actionable knowledge. It provides a roadmap from understanding the business problem all the way to communicating the results and deploying solutions. The life cycle is not just an academic theory. In every real world data science project I have encountered or read about, this life cycle or some variation of it is followed. It keeps teams aligned, projects on track, and delivers focused. The life cycle consists of 5 major phases. First one is data discovery, and the second one is data preparation. Third one is model planning. Fourth is model building. Fifth is communicate results. Let's walk through each one in detail. Phase 1, Data Discovery. Data discovery involves developing a clear understanding of 5 things: the business problem you are trying to solve, the available data sources, the data formats in which data exists, initial hypothesis about what might be true, and the scope and constraints of the project. The specific activities in data discovery include identifying internal and external sources, collecting sample data sets to understand what you are working with, checking data types, is the data numerical, categorical, ordinal, or date time, identifying quality problems, is the data missing, noisy, or inconsistent, assessing the 3 V's of big data: volume, how much, velocity, how fast, and variety, what kinds, and conducting an initial exploratory analysis. The outcome of data discovery is a clear problem to data mapping. You know what exactly the problem you are solving is and exactly what data you have to work with. Let's go deeper into problem understanding. In data science, we define the problem formally as a mathematical mapping. F function x tends to y, where x is the input space, your predictor variables, the features you will use to make predictions, and the y is the target variable, what you are trying to predict or classify. During this phase, you identify what kind of problem you are dealing with. If y is continuous, for example, predicting someone's salary or the price of a house, that's regression problem. If y is categorical, for example, predicting whether an email is spam or not, that's classification problem. If there is no target variable and you're trying to find natural groupings in the data, that's a clustering problem, which is unsupervised learning. This classification of your problem directly determines which algorithm and evaluation metrics you will use. So, getting this right at the discovery stage is absolutely critical. Once you understand the problem, the next step is identifying your data sources. Data comes in three fundamental structures: structured data, unstructured data, and semi structured data. Structured data. This comes from relational database management systems or RDBMS. These are schema based tables with ACID properties: atomicity, consistency, isolation, durability. Examples are SQL. This is the easiest type of data to work with. Now it comes to semi-structured data. This includes JSON and XML formats. These have tree-like hierarchies but no rigid schema. They are stored in document databases like MongoDB. You will encounter this frequently when working with APIs. Now coming to unstructured data. This includes images, audio, and text. These require feature extraction before machine learning can be applied. They are also high dimensional, meaning they can have a very large number of features, which leads to what is called the curse of dimensionality, a challenge we'll address when they discuss feature selection. Understanding the structure of your data sources determines the pre processing techniques you will need to apply. Now we move into phase 2, data preparation. Data preparation is arguably the most time consuming and critically important phase in the entire life cycle. Data preparation makes raw data suitable for modeling. It has four major components: data cleaning, fixing errors in the data, handling missing and noisy data, dealing with the gaps and distortions, transformation, reshaping and scaling the data, feature selection, choosing the most informative variables. Remember our earlier analogy? Data preparation is like cooking, right? Before you cook, you wash your vegetables, cut them into size, and prepare your spices. If you skip this step and throw raw, dirty ingredients into the pot, the meal will be terrible. Similarly, skipping data preparation leads to the bad models. Let's start with data cleaning. Real world data is messy, and I mean genuinely frustratingly messy. Here's what you will typically find in raw data: missing values, duplicates, noisy data, wrong format, outliers, inconsistent data, typo errors. If you don't clean this data, your analysis and machine learning results become incorrect or misleading. This is the garbage in, garbage out principle. Here's a concrete example from this slide. If a salary column contains values like 25,000, 26,000, 27,000, and then suddenly 1 crore 20 lakhs, then last value is likely an entry error or an outlier. If you feed this into a machine learning model without addressing it, the model will be severely biased towards the extreme value. The goal of data cleaning is to improve data quality and integrity. Let me give you a quick but important reference on the types of data which is dirty you will encounter and where it comes from. Types of problems: missing values shown as NaN or blank, noise, for example, sensor fluctuations in IoT data, inconsistency, the same gender might be recorded as MALE, capital M, or small MALE or capital MALE in the same dataset, duplicates, repeated customer records, and outliers, values far from the distribution. Sources of dirty data include human entry mistakes, server logs, sensor readings, survey responses, online forms, web scraped data, and transaction systems. Each of these sources introduces its own characteristic type of error. Understanding the source of your data helps you anticipate and address the types of errors you are likely to find. Now let's talk about one of the most unannounced topics in data preparation: handling missing values. Not all missing data is the same. There are three types of missingness and each requires a different treatment strategy. Type 1 MCAR, missing completely at random. Missing values occur with no pattern whatsoever, completely independent of any other variable. Example: a lab assistant accidentally drops a test tube and loses one sample. There is absolutely no relationship with the patient's data. When data is MCAR, the simplest deletion or imputation methods work fine. Type 2 MAR, missing at random. Missingness depends on observed variables but not on the value of the missing variable itself. For example, men might be less likely to respond to health surveys, so gender, an observed variable, predicts missingness, but the missing health value itself doesn't determine whether it's missing. Type 3 MNAR, missing not at random. This is the most problematic case. Missingness depends on the missing value itself. A classic, a classic example: a person who is depressed is more likely to skip questions about depression, or people with very high income are more likely to avoid reporting it. MNAR is dangerous because the missing data is systematically biased and it requires model based correction strategies to handle properly. Now, let's look at the first major category of strategies for handling missing values: deletion methods. These are used when the percentage of missing data is small, typically less than 5%, and the data is missing at random. Method 1: row deletion, also called as list-wise deletion. Remove entire rows that contain missing values. The advantage is simplicity. The disadvantage is that it reduces your dataset size. If n is your original number of rows and k rows have missing values, your dataset has n minus k rows. If your dataset is small, this can be a significant loss. Example: if age is missing in row 2, that entire row is deleted. Method 2: feature deletion. Drop an entire column if it has too many missing values, typically more than 50 to 60%. The risk here is that you might accidentally remove a feature that was actually predictive. So use this with caution only when the column is overwhelming missing and unlikely to be recoverable. Example: if the blood group column is missing for almost every patient, it gets dropped. Method 3: pairwise deletion. Used specifically in statistical correlations. Instead of deleting entire rows, you'll only use the available pairs of values for each specific calculation. This preserves more data, but it can introduce complexity because different calculations may use different subset of rows. Example: if you have x and y values, but y is missing in row 2, you compute the correlation using only the rows where both x and y are present. Rows 1 and 3 are example. This is the example for row deletion. Remove row if missing value is critical. Now row 2 is deleted here in this table. This is the example for feature deletion. Here in the blood group, the entire column is dropped. When it comes to pairwise deletion, the correlation using only pairs where both variables are present. So here the correlation computed using rows 1 and 3 only. Since in row 2 there is a missing value. When deletion isn't appropriate, especially when you have too much missing data to afford losing rows, you turn to imputation. Imputation means filling in the missing values with estimated values. The first category is unvariate imputation. Methods that use only one column's information to fill in missing values. Method 1. Mean imputation. Use the average of all existing values to fill in missing ones. Best for symmetric continuous data without outliers. Example, salaries are 40, 50, 60 and a missing value 70. Mean is 55. Replace that missing value with 55. Here we can see that. Now method 2 is median imputation. Use the middle value instead of the mean. Best for skewed data or data with outliers. Because the median is not affected by extreme values the way the mean is. Now coming to method 3, mode imputation. Mode imputation used for categorical variables. You fill the missing value with the most frequently occurring category. Example, gender values are M, F, M and a missing value. The mode is M. So the missing value gets replaced with M. Now coming to method 4, constant or zero imputation. Replace missing values with a fixed constant, often 0 or a placeholder unlike unknown. Useful for space data where 0 is meaningful value or the text fields where unknown is acceptable placeholder. Here we can see the examples as I have mentioned before. Now let's move to more powerful multivariate imputation methods, that is KNN imputation. Methods that use multiple columns of information to estimate missing values. The first one is KNN imputation. KNN stands for K nearest neighbors. The idea is elegant. To fill in a missing value in a row, we find the K rows that are most similar to the row with the missing value and use their values to estimate what's missing. Here's how it works step by step. Step 1. Compute distances from the row with the missing value to all the other rows. We typically use Euclidean distance, the straight line distance in multi-dimensional space. Step 2. Rank the distances from smallest to longest. The smallest distance means most similar. Step 3. Select the k nearest neighbors, the k rows with the smallest distances. Step 4. Take the mean of their values for numerical features or the mode for categorical features and use that as imputed value. Now, uh, just take an example. We have a data set with height, weight and age. Now row 6 has height 178, weight 72 and age as missing. Using k is equal to 3, we find the three nearest rows by distance. Their ages are 32, 36 and 29. Mean of these ages are approximately 32.3. So we impute the age as 32 for row 6. KNN imputation is excellent when variables have non-linear relationships and have the dataset is small to medium in size. However, it is computationally expensive for very large datasets because you have to compute distances to every row. The second multivariate imputation method is linear regression imputation. Here, instead of finding neighbors, we build a regression model to predict the missing value. The model learns the relationship between the missing variable and the other variables. The general form is y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus and so on, which is the standard linear regression equation. The closed form solution is beta is equal to x power t x whole power minus 1 x power t into y. This is the ordinary least squares formula. Let me walk you through a concrete example. We have height, weight and age. Age is missing for one row. We build a regression model. Age is equal to a plus b into height. Step 1. Compute means. Mean height is equal to 170. Mean age is equal to 29.4. Now step 2. Compute the slope b using formula. We get b as 0.62. Now coming to step 3. Compute the intercept. A is equal to 29.4 minus 0.62 into 170, which is minus 76. So our regression equation is age is equal to minus 72 plus 0.62 into height. Step 4. For the missing row with height is equal to 178, age is equal to minus 76 plus 0.62 into 178, which is substituting the height value in the regression equation. So we will get 34 approximately. This is more accurate than simple mean imputation because it captures the relationship between height and age. But here's an important nouns. Regression imputation assumes that the predictor variable you choose has high correlation with the missing variable. So before choosing which variable to use as a predictor, you must check the correlation. If height has correlation 0.82 with age and weight has only 0.30, use height. If the situation is reversed, use weight. And if both correlate strongly, use multiple linear regression, which is age is equal to b naught plus b1 into height plus b2 into weight. This gives the most accurate imputation. Excellent. Now let's move to the next major component of data preparation. These are the cases which I have mentioned before. If height correlates strongly with the age, if weight correlates strongly with the age, if both correlates, then use multiple regression. These are the formulas which are used. Now the major component of the data preparation is transformation. Transformation modifies the data by changing its scale, distribution or representation so that algorithms can learn patterns better. Why do we need transformation? There are several compelling reasons. Machine learning models perform better when features are on similar scales. If one feature ranges from 0 to 1 and another ranges from 0 to 10 lakhs, the model will incorrectly place more importance on the feature with the larger range. Transformation also reduces skewness, helping algorithms that assume normally distributed data. It reduces noise and variability, making the data cleaner. It handles outliers. It prepares data for distance based algorithms like KNN, SVM, and K means, which are fundamentally based on calculating distances between data points. And it improves training stability for neural networks which are sensitive to scale of input features. There are three main types of transformation that we'll cover. The first one is smoothing, second one is aggregation, third one is normalization. Smoothing reducing the noise or randomness in data, and aggregation is used for combining multiple values into a single representative value, and normalization, which is also called as scaling, is used for scaling the features to similar ranges. Let's go through each one now. Smoothing. Smoothing is a transformation technique used to reduce noise or randomness in data, particularly in time series data. There are three methods in this smoothing: moving average, exponential smoothing, binning based smoothing. Method 1: moving average smoothing. Replace each data point with the average of values in a short time window. The example is raw RPM sensor readings from a machine are 3000, 3050, 4500, 3100, and 2950 and 2900. Notice that 4500 is a spike, clearly caused by sensor noise. Applying a 3-point moving average, the first window 3000 plus 3050 plus 4500, which is first three values, is divided by 3. Then we will get the approximate value as 3517. The second window is 3050 plus 4500 plus 3100 whole divided by 3, which we will get the value as 3550 as approximate, and so on. The result is a smooth trend that moves the spike. This is incredibly useful in IoT sensor data, manufacturing stock prices, and an application where you need to see underlying trends rather than any noise fluctuations. When it comes to method 2, this is the example I have mentioned before. When it comes to method 2, exponential smoothing, this is more sophisticated. It weighs recent values more than older values. The formula is St is equals to alpha xt plus 1 minus alpha into St minus 1, where St is the smoothed value at time t, xt is the actual value at time t, and alpha is the smoothing factor, and alpha ranges between 0 and 1. Higher alpha is means reacts faster, lower alpha means reacts lag. That means more smooth but lag increases. With alpha is equal to 0.3, recent values get 30% weight and the previous smoothed value carries 70% weight. This means older values still influence the output, but their influence decays exponentially over time. This is the example with RPM data. S1 is equal to 3000. S2 can be calculated as 0.3 into 3100 plus 0.7 into 3000, which gives 3030. And similarly, S3, S4, S5 can be calculated. So as we can see the comparison table, raw versus smoothed. This is the raw RPM and this is the smoothed RPM, which is calculated before. As it is mentioned here, in the interpretation, the raw data jumps up and down. The smoothed values follow the trend without chasing spikes. Outliers have less impact as time progress. And the method 3 is binning based smoothing. Here data is divided into bins, that means intervals, and values within each bin are replaced by the bin's mean, median, or nearest boundary. For example, the data is given as 4, 6, 7, 10, 12, 15, 18, 19, 21, 24. Now we want to smooth using binning method with 3 bins. Now step 1, divide the data into bins. Since given the number of bins is equal to 3, each bin size is calculated as total data points divided by number of bins. That means 10 divided by 3 as in between 3 and 4. That means each bin should contain maximum 4 and minimum 3 values. Bin 1 contains 4, 6, 7. Bin 2 contains 10, 12, 15. And bin 3 contains 18, 19, 21 and 24. Now step 2. Smooth the bins. Find the means of each bins. Bin 1 mean and bin 2 mean and bin 3 mean. Round it to nearest value. Now the smooth data will be the means. That means here this is the bin 1, this is bin 2 and this is bin 3. Bin 1 mean is found as 6 and bin 2 mean is found to be 12 and bin 3 mean is found to be 21. That is mean smoothing. Now using median smoothing we will find the middle values. Now the median of bin 1 becomes 6, bin 2 becomes 12 and bin 3 becomes 20. According to that, we will write the smoothed data as 6, 6, 6, 12, 12, 12, 20, 20, 20, 20. And the other method is boundary smoothing. Replace with closest bin boundary. Each value is replaced by the nearest bin boundary, minimum or maximum value. Here in bin 1, 4 is minimum value and 7 is the maximum value. So we will write the value which is closest to 6, that is 7. So in bin 2 the minimum value is 10 and maximum value is 15. Now 15 is closer, 10 is closer to 12. So we will write 10. In bin 3, the minimum value is 18 and maximum value is 24. Now, the smoothed data is 4, 7, 7, 10, 10, and 15, 18, 18, and 24. Now, coming to types of transformations. Second method, aggregation, combining multiple values into a single value. Examples you encounter every day, summing daily sales figures into weekly totals and then weekly totals into monthly figures. Averaging IoT sensor readings over a time window to reduce data flow. Grouping hospital records by patient to create a single summary record per patient. Why is aggregation useful? It reduces data science dramatically, making computation faster and storage requirements smaller. It also improves computational efficiency faster and because algorithms work on fewer, more meaningful data points rather than millions of raw observations. Aggregation is foundational in data warehousing and business intelligence. The ETL process almost always includes aggregation steps. Now, the third one is normalization. It is also most important transformation technique for machine learning, which is also called as scaling. Normalization scales numeric attributes to a common scale without distorting the relationships among values. It's applied when different features have different ranges or units. For example, age in years, glucose level in mg or dl, and income in rupees, and all on completely different scales. Now, why is this required? Distance based algorithms like KNN, K means, SVM, and neural networks are extremely sensitive to the scale of features. Without normalization, a feature with a range of 10,000 will dominate a feature with a range of 10. Even if the smaller range feature is actually more informative, it affects dominance of large range features and improves interpretability. Let's look at the three main normalization techniques. Technique 1, minimum maximum normalization. It maps values to the range 0 and 1. The formula is x dash is equal to x minus x mean by x maximum minus x minimum. For example, glucose values are given as 200, 185, 170 and 220. The minimum value is 170 and the maximum value is 220. For the value 200, we can find the x dash value which tends to 0.6. So 200 becomes 0.6 in the normalized scale. Characteristics are preserves the distribution shape but sensitive to outliers. An extreme outlier will compress all other values into a very narrow range. Now coming to technique 2, Z-score normalization, which is also called as standardization. Transforms data to have mean is equal to 0 and standard deviation is equal to 1. The formula is given as x minus mean by standard deviation. For example, the weight is given as 60, 70 and 80 and the mean is given as 70 and standard deviation is given as 10. For value 80, we can find the z-score normalization by using the formula z is equal to x minus mu by sigma, which gives 1. The characteristics of z-score normalization is handles outliers better than minimum maximum and used in PCA SPM regression models. Now coming to technique 3, decimal scaling. It moves the decimal point by dividing a power of 10. Formula is given as x dash is equal to x by 10 power j, where j is chosen to make the values fall between minus 1 and 1. Example, 50,000 is given as j is equal to 5 That gives 50,000 divided by 10 power 5, which gives 0.5 as answer. It is simple but effective for quick baselines. The final major component of data preparation is feature selection. Feature selection is the process of choosing the most relevant features from your dataset and removing the irrelevant or redundant ones. It reduces dimensionality, the number of input variables, while preserving or even improving model performance. Why does this matter? More features don't always mean a better model. In fact, too many features can lead to overfitting when the model memorizes the training data. Instead of learning generable patterns, it increases the computational costs. The training becomes slower. Introduce the curse of dimensionality. In high dimensional spaces, data becomes increasingly sparse, making it hard for algorithms to find patterns. Feature selection addresses all of these problems. There are two main categories of feature selection methods. Let's start with the filter methods. Filter methods select before model training using statistical measures. They are fast, model independent, meaning they don't depend on any specific algorithm, and they are the first line of defense in feature selection. Filter method 1. The filter method 1 is given as variance inflation factor or variance threshold, which is called VIF. This removes features with low variance. If a feature has the same or nearly the same value for all samples, it contributes no information. It can't help the model distinguish different outcomes. For example, if every patient in your dataset is from the same city, city is useless as feature. Now coming to filter 2, correlation based selection. It keeps features that are highly correlated with the target and have low correlation among themselves. We want features that tell us something about Y, but that aren't just duplicating information that other features already capture. Coming to filter method 3, entropy based selection. This is used for classification problems. Information gain measures how much information a feature contributes to predicting the class. The formula is given as ig y comma x is equal to h of y minus h of y by x. It is used in decision trees feature ranking. Now, decision trees are critical topic in this module. Now, as I have mentioned earlier, variance threshold based selection. It features with very low variance, that means very little variation, and do not contribute much information towards prediction. High variance features gives more information as we can see in this table. Ignore or remove low variance or non-informative features. The benefits of removing such features are simplifies the model, reduces noise and dimensionality, improves training speed, but ignores relationship with target. In this, the formula is given as variance of x is equal to 1 by n summation of n of xi minus mu whole square. When it comes to correlation based feature selection, it selects features by analyzing linear relationships with target or with other features. It keeps relevant, that means non redundant, and removes highly correlated features, that means redundant, and weakly correlated features with the target. Here, marks and grade are highly correlated. As we can see here, the values are approximately same. So keep marks and remove grade. Attendance and study hours are non-redundant. So selected features are marks, attendance and study hours. Now in entropy based selection, we use the formula as minus summation of pi log pi to the base 2. And info gain ig of target comma feature is calculated as entropy of target minus entropy of target by feature. And this is the example problem. In this table, as we can see, the number of passing students is 2 and the number of failing students is 3. So the total number of passing and failing students are 5. Now the probability of passing students is 2 by 5 and the probability of failing students is 3 by 5. Now the entropy of result is calculated as minus summation of pi log pi to the base 2. Now we will calculate the entropy for the result as according to these probabilities, and we will get the entropy of the result as 0.971. Now calculate the entropy for high marks and low marks. So as a result, the entropy of marks is given as 0.551. Now from that calculate the information gain of both result and marks, and that we will get as 0.420. Now coming to decision tree. The decision tree are critical topic in this module and they connect directly to feature selection. A decision tree is a machine learning model that makes decisions by asking a sequence of questions about features. At each node, it selects the feature that best separates the data. Using Gini impurity or entropy and information gain, the tree-like structure has a root node at the top representing the first and most important split. Internal nodes representing subsequent decision points, branches representing the outcomes of each decision, and leaf nodes at the bottom representing the final predictions. And this is the decision tree for the above given data. As I have mentioned, the key components of decision tree are root node, internal nodes, branches, and leaf nodes. As I have mentioned earlier, how decision trees work: selecting the best split, Gini impurity, entropy, information gain, and mean squared error MSE. Then splitting the data set, then recursion, and stopping the criteria. Now coming to ID3 algorithm. The ID3 algorithm, it is one of the most famous decision tree algorithms developed by Rose Quinlan. Builds trees by recursively selecting the attribute with the highest information gain at each step. Let me walk you through it. First, calculate the entropy of the target class. Second, for each feature, calculate the information gain of splitting on that feature. Third, choose the feature with the highest information gain as the split point. Fourth, create subtrees recursively. Fifth, stop when all the data in a node belongs to a single class or there is no more features to split on. The classic example is, yeah, these are the steps to calculate ID3. And the classic example is play tennis dataset using weather, sunny or overcast or rain, and information and temperature of hot or mild or cool to predict whether someone plays tennis. We calculate information gain for both features. Overcast weather always leads to yes, so it becomes a leaf node directly. Sunny and rainy conditions require further splitting by temperature. The result is a tree that correctly classifies 14 training examples using a logical interpretable rules. The second category of feature selection methods is wrapper methods. Unlike filter methods, wrapper methods use model performance as their criteria for selecting features. They try different subsets of featuring, train a model on each subset, and keep the subset that gives the best performance. There are three main wrapper methods. They are forward selection, backward elimination, and stepwise selection. For forward selection, it starts with no features, an empty model. Then iteratively add the features that most improves model performance. Repeat until adding more features doesn't help. This builds up from nothing. As we can see, stop when accuracy no longer improves. So the selected features are marks, study hours, and attendance. Now coming to backward elimination. Starts with all features, then iteratively remove the least useful feature. Repeat until removing more features starts hurting performance. This tears down from everything. As we can see from this table, the selected features are marks, study hours, and attendance. As there is no change in the student ID and no change in the gender, and attendance drops accuracy. Now this stepwise selection. It is also called as combined forward selection and backward elimination. A combination of forward selection and backward elimination, you can address features but also remove previously added features if they become redundant as new features are added. This dynamic approach is often more accurate than purely forward or backward methods. The downside of wrapper methods, they are computationally expensive, especially with larger feature sets because you're training a model for every subset you test. Now let's talk about the two fundamental concepts that underpin all feature selection: relevance and redundancy. Relevance. How useful is a feature for predicting the target? A feature is strongly relevant if it is necessary for prediction. Removing it causes a significant drop in model accuracy. Example: in featuring a diabetes or predicting diabetes, glucose level is strongly relevant. A feature is weakly relevant if it has some predictive power, but the same information might already be captured by other features. Example: weight might be weakly relevant if BMI and age already encode similar information. A feature is irrelevant if it has no meaningful relationship with the target. Example: patient registration number or hospital room number. These have zero predictive power for health outcomes. How do we measure relevance? For numerical features, compute the Pearson correlation with the target. For categorical features, use chi-square test. For classification problems, use information gain or mutual information. Redundancy. Is this feature just duplicating information already captured elsewhere? A feature is redundant if another feature already captures the same information. Example: height in centimeters. Example: height in centimeters, height in inches. These two give the same information, so one is redundant. And the most realistic example is BMI, weight and height. Since BMI is literally calculated from height and weight, having all three is highly redundant. How do we measure redundancy? Compute correlation between features. If the correlation mod R is greater than zero point 0.8, then it is high accuracy. Consider removing one. We can also use the variance inflation factor VIF greater than 10 indicates multicollinearity. Strong redundancy between features and mutual information between features captures non-linear redundancy. The goal of feature selection is to find that are highly relevant to target and low in redundancy with each other. This combination gives the most informative efficient feature set for building models. Excellent. We have thoroughly covered data discovery and data preparation. Now let's move to phase 3, model planning. Model planning is a strategic thinking phase that happens before you start training any algorithm it involves. Selecting algorithms are based on your problem type. Is it regression, classification, or clustering? You choose appropriate algorithms. Regression for continuous targets, classification algorithms like decision trees, and SVM for categorical targets, clustering for unsupervised problems, and data partitioning, deciding how to split your data into training, testing, and validation sets. A common split is 80% training and 20% testing. For smaller datasets, cross validation is preferred. Assumptions and constraints. Every algorithm has assumptions. Linear regression assumes a linear relationship between features and target. If these assumptions are violated, the algorithm will perform poorly. Identifying these constraints upfront saves a lot of waste efforts. Feature engineering decisions. Planning what new features might be useful to create from existing ones. Performance metrics definition. Deciding upfront how you will measure success. For regression, MAE, MSE, RMSE, R square. For classification, accuracy, precision, recall, F1 score, AUC, and ROC. Defining metrics before modeling prevents the temptation of choosing metrics that make your model look good rather than actually performing well. Now, coming to phase 4, model building. This is where the machine learning actually happens. The workflow in model building follows this sequence: collecting data, cleaning and pre processing the data, split into train and test, choosing an algorithm, training the model, generate predictions. Then critically you evaluate those predictions against the actual values using your predefined metrics. If performance is unsatisfactory, you iterate, try different algorithms, engineer new features, adjust hyperparameters, and repeat. Model building is fundamentally iterative. Rarely does the first model you try turn out to be the best one. Now, coming to phase 5, model evaluation. How do we know if our model is actually good? Evaluation depends critically on the type of problem you're solving. Regression problems, where you predict continuous values like price, age, or salary. Classification problems, where you predict categories like yes or no, pass or fail, or cancer or no cancer. Using the wrong evaluation metric can give you a false sense of how well your model is performing. So, choosing the right metric for your problem type is very crucial. Let's dive into the classification metrics. Starting with the confusion matrix, which is the foundation of all classification evaluation. The confusion matrix is a table with the four cells: true positive, predicted positive, actually positive, correct; true negatives, predicted negative, actually negative, correct; false positives, predicted positive, actually negative, and wrong. Also, type 1 error, false negatives, predicted negative, actually positive, wrong, also called type 2 error. Here, false positives are called as type 1 errors and false negative are called as type 2 errors. From these four values, we derive all classification metrics. Now, accuracy, the formula is given as TP plus TN by total. That means true positive plus true negative divided by total. This measures the overall proportion of correct predictions. Example, with TP is equal to 40 and TN is equal to 50 and FP is equal to 5 and FN is equal to 5, the accuracy is calculated as TP plus TN, that means 40 plus 50 by total, that means 40 plus 50 plus 5 plus 5, which is given as 90%. Warning: the accuracy can be misleading with imbalanced datasets. If 95% of your data is one class, a model that always predicts that class gets 95% accuracy without learning anything useful. Now, coming to precision. The formula for precision is given as true positive by true positive plus false positive. That means out of all the times the model predicted positive, how many were actually positive? This measures the reliability of positive predictions. Coming to negative predictive value, it is the formula is given as true negative by true negative plus false negative. Out of all predictions of negative, how many were actually negative? This is the opposite of precision for negative class. Here the precision is given as accuracy on positive predictions and recall is given as accuracy on positive instances in dataset. And the formula for recall is given as TP by TP plus Fn. That means true positive by true positive plus false negative. Out of all the actual positives in the dataset, how many did the model find? High recall means the model doesn't miss any positives. When it comes to specificity, the formula is given as true negative by true negative plus false positive. Out of all actual negatives, how many did the model correctly identify as negative? This is the opposite of recall. It measures performance on the negative class. Coming to balanced accuracy. The average of recall and specificity is called balanced accuracy. This is a more fair measure than simple accuracy for imbalanced datasets. Coming to F1 score. The formula for F1 score is given as 2 into precision into recall divided by precision plus recall. The harmonic mean of precision and recall is called as F1 score. F1 provides a balanced measure between the two, useful when you care equally about avoiding false positives and false negatives. A high F1 score requires both precision and recall to be high. AUC and ROC is given as area under the receiver operating characteristic curve. It measures the ability to distinguish classes. Higher is better. Now, let's talk about the classification matrix formulas. And this is the example values. Here the sensitivity is given as TP by TP plus Fn and specificity is given as Tn by Tn plus Fp and accuracy is given as TP plus Tn by TP plus Tn plus Fp plus Fn and negative predictive value is given as Tn by Tn plus Fn and precision is given as Tp by Tp plus Fp. Here it is true positive, false negative, false positive and true negative. These are the example values. Now, let's talk about the specifically about the ROC curve, the receiver operating characteristic curve. The ROC curve plots the false positive rate on the x-axis against the true positive rate recall on the y-axis as the classification threshold is varied. True positive rate is equal to Tp by Tp plus Fn, this is recall, and false positive rate is given as Fp by Fp plus Tn, which is 1 minus specificity. If values on the x-axis FPR are small, it means low false positives and high true negatives. Here we can see that if values on the y-axis TPR are large, it means high true positives and low false negatives. The ideal point is the top left corner of the ROC plot. FPR is equal to 0, TPR is equal to 1. Perfect discrimination. The relationship between FPR and specificity is inverse. FPR is equal to 1 minus specificity. If your test is 90% specific, its FPR is 10%. A high specificity means low false positive rate, fewer false alarms. Why is ROC curve valuable? Because precision and recall are calculated at a single threshold. The ROC curve shows model performance across all thresholds, giving you a complete picture of the trade-off between catching positives and avoiding false alarms. Here it is the practical example. In a medical diagnosis model, setting a low threshold catches more true positives but also generates more false positives. The ROC curve helps you to find the optimal threshold for your specific use case. Now let's cover the regression metrics. There are four common regression metrics. They are mean squared error MSE, root mean squared error RMSE, and mean absolute error MAE, and R squared R square. Coming to MAE, mean absolute error. It is the average absolute difference between predictions and actuals, which is easy to interpret. The average of the absolute differences between predicted and actual values. It's easy to interpret because it's in the same units as the target variables. If you are predicting house prices and MAE is equal to 5 lakh, that means your predictions are off by 5 lakhs on average. MAE treats all errors equally. When it comes to MSE, mean squared error, the average of squared differences between the predicted and actual values. Because errors are squared, larger errors are penalized more heavily. This makes MSE sensitive to outliers. If one prediction is wildly wrong, it has more disproportionate effect on MSE. Coming to root mean square error RMSE. The root mean square error brings the metric back to the same units as the target variable, making it easier to interpret than raw MSE while retaining the property of penalizing large errors more. Let me do the worked example from the slide. As it has given, the actual values are 15, 25, 35, 45 and 55, and predicted values are 18, 22, 38 and 42 and 52. The squared differences are 15 minus 18 whole square, 25 minus 22 whole square, 35 minus 38 whole square, 45 minus 42 whole square, and 55 minus 52 whole square, which gives a values of all the values of 9. Now compute the MSE. MSE is equal to 9 plus 9 plus 9 plus 9 plus 9 divided by 5, which is 45 by 5, which is 9. Now calculate the RMSE. RMSE is equal to square root of MSE, which is square root of 9, which we get as 3. So, on average, the model's predictions are 3 units away from the actual values. Now coming to R squared. The proportion of variance in the target variable that is explained by the model range 0 to 1. R square is equal to 1 means the model explains all the variance, perfect fit. R square is equal to 0 means the model explains nothing. No better than just predicting the mean. Higher R square is better. And the formula is given as R square is equal to 1 minus RSS by TSS, where RSS is equal to sum of squares of residuals and TSS is total sum of squares. We can also write it as R square is equal to 1 minus summation of yi cap minus yi whole square by summation of yi minus yi bar whole square. And the final one is adjusted R squared. R square adjusted for the number of predictors, better for comparing models. Adjusted R square penalizes you for adding unhelpful features. It's better for comparing models with different number of features, and the formula is given as R square adjusted is equal to 1 minus of 1 minus R square into n minus 1 by n minus p minus 1, where R square is R squared, n is number of samples or rows in the dataset, and p is the number of predictors or features.